In this video, we're going to look at linear approximation. So let's start off with the linear approximation formula. So it says f of x plus dx, comma y plus dy is approximately equal to f of xy plus df. This df here is the differential of f, and it's helpful to have watched the previous videos on differentials before we jump into this linear approximation process. So this approximation is better the closer dx and dy are to 0. And just to give you a little insight where this formula comes from, basically if we move the f of xy over to the left side, then we'd have something like f of x plus dx, y plus dy minus f of xy is approximately equal to df. And that makes sense because this whole left side here is just the delta f that we were talking about in the previous video. So it's the change in f values between two nearby points. So really, linear approximation is just a rephrasing of that geometric idea from differentials and then rearranging. So here's our problem. We've got a multivariable function, f equals square root of xy, and we want to approximate the value of our function f when x is equal to 3.9 and y is equal to 1.2. We're going to do that using differentials. So I have to say that this, this application is not so directly useful. I mean, if I wanted to know the value of the function, I'm pretty sure I would just go grab a calculator and calculate it. But what this does is it sets us up really nicely for the discussion of calculating error that we're going to have over the next few videos. So let's think of this example as just helping us get familiar with differentials before we can do something a bit more interesting. So the idea is that we want to approximate the value of our function at some messy numbers. So what we're going to do here is we're going to choose some nice values of x and y that are close to the values at which we want to do, where we want to do the approximation. So you could say x equal 3.9, that's pretty close to x equal 4. X equal 4 is a really nice value going into the square root function. And similarly, we could say, if we want to approximate near y equal 1.2, maybe choosing y equal 1 would work nicely. So x and y, nice values, meaning values that work out well when you put them into your function. And you want that to be near the point at which you're doing the estimation. Okay, and then let's think about dx and dy. So dx and dy, you could think of them as the change in the x value as we're moving from x equal 4 to x equal 3.9, or from y equal 1 to y equal 1.2. So let's look at dx first. Okay, so imagine that we're stepping from the nice value over to the messy value. So the change in x would be 3.9 minus 4, which is minus 0.1. And then for dy, stepping from the nice value to the messy value, so your net change in y would be 1.2 minus 1 is 0.2. Okay, so there we have the values of x, y, and their differentials. And from there, we can jump into the differential formula and just try to calculate df. So df, as we saw in our previous video, f sub x times dx plus f sub y times dy. That means we're going to need to take partial derivatives of our function f here. And one little trick to make this calculation a little bit easier, for this particular function, remember that a product under the square root can be thought of as a product of roots. So we might find it a little easier to think of f as root x, root y, just for the sake of calculating the partial derivatives. Okay, so let's get df calculated. So for f sub x, y is going to be a constant. So we're going to have the root y staying in place, and then the derivative of the root x is 1 over 2 root x. So that gives us our first term. And then for f sub y, x is being treated as a constant, so the root x is going to stay where it is. And then the derivative of root y gives us 1 over 2 root y. So there we go. There's our differential of f. we're going to try plugging in our values here. We know x, y, and the values of those differentials. So let's just get a value for df. All right, so subbing everything in, we're going to have 1 over 4, because on the bottom here we've got 2 times, basically another 2 gives us a 1/4 there, times our dx minus 0.1. Plus, for the second term, we're going to have 2 over 2, which is 1, times 0.2. Okay, so value of df coming up here, it's 0.175. So now let's finish off our calculation. I'm going to write down our linear approximation formula again, and we'll figure out how that applies in this specific case. So linear approximation formula says f of x plus dx, y plus dy is approximately equal to f of xy plus df. And the context here is that x and y are some nice numbers. So this number on the right side, typically easy to calculate. And then think of the x plus dx, y plus dy as being the messy numbers. So we're approximating f at some coordinates that are, not necessarily clean numbers. So in this case, we're saying f of 3.9, 1.2 is what we're trying to calculate. We're going to say that's approximately equal to f of 4, 1 plus the df that we've just calculated using those x and y values. So our df was 0.175, and we can just finish off here. Okay, let's evaluate f at 4, 1. Just scrolling back up here. Remember, f was square root of xy. So if we plug x equal 4, y equal 1 into that, we get 2. In other words, that 2 plus 0.175, or in other words, 2.175 is the approximate value of f of 3.9, 1.2. You could always plug that into your calculator and check that our answer's coming out reasonably close to the true answer. So again, this calculation, not so directly useful, but it sets us up really nicely for the discussion around error that we're going to have over the next 2 videos. Thanks for watching.